Exploring polynomial functions. For this one, we're going to start with some terminology. So a polynomial function is a function that can be written in the following form. F of x equals a sub n, x to the exponent n, plus a sub n minus 1, x to the exponent n minus 1, a sub n minus 2, x to the exponent n minus 2, all the way down to a constant. First of all, what is a? Well, a sub I, whereas n minus 1, and so on. So a sub I is equal to any real number. Any number you want to throw in front of the variable. A fraction, a decimal, an integer value, it doesn't matter. So n, or the exponent, is any number greater than 0. So let's take a look at a few examples. For example, we have f of x equals 2x minus 3. Notice our exponent is 1 on this polynomial function. We can also have g of x here, which is 4x to the exponent 7 plus 6x to the exponent 5 minus root 3x. Again, we can have any real number for the coefficient. And finally, h of x equals 1 minus x plus 3x squared plus 4x to the exponent of 6 and minus 7x to the exponent of 4. That is also a polynomial. So what are examples of objects that are not polynomials? So some that you've seen before. We can have our square root function, which is the same thing as x to the exponent 1/2. Notice the exponent is not an integer value. We've also seen our reciprocal function, 1 over x, which is the same thing as x to the minus 1. So that's a negative exponent, which means it's not a polynomial. When a polynomial is written in expanded form, with decreasing powers of the variable, it is said to be in what we call standard form. And from our 3 examples above, we see that f of x is in standard form. We also see that g of x is in standard form. However, h of x is not, because the terms of that polynomial are not starting with the highest exponent and going down to the lowest. The degree of a polynomial is the value of the highest exponent on a variable when the polynomial is in expanded form. So if you look back to our 3 examples, f of x we see has a degree of 1. That's the exponent on the x. G of x has a degree of 7. That is the highest exponent on the x term, 4x to the exponent 7. And h of x, the degree is 6. It is the highest exponent in that expression. So next up is leading coefficient. So leading coefficient is the coefficient of the term with the highest exponent. So we need to look for the term that has the highest exponent and then state its coefficient. And again, when the polynomial is in expanded form. So for example, the leading coefficient for f of x. So the coefficient for f of x is 2, since it has the coefficient of 2 in front of the x. For g of x, the leading term is 4x to the exponent 7, and the coefficient for that term is 4. And finally, for h of x, the leading term is 4x to the exponent 6, and the coefficient for that term is 4. It's the number in front of the variable. Lastly, polynomial functions are continuous. That is, you can graph the polynomial function without having to lift your pencil off the paper. So for this unit, all the functions we will look at will be continuous functions. Next up is what I call a difference table. So if you want to find the differences for a set of points, you take the y2 minus the y1. So I like to cross out the first box of this table and write 1 minus 4, which tells me that my first differences, or my delta y, is equal to negative 3. And then we continue. 0 minus 1, that equals negative 1. 1 minus 0, that equals 1. 4 minus 1 is 3. And 9 minus 4 is 5. So these are called the first differences. And since the first differences vary, we know that this is a non-linear relationship. So what we can do now is take a look at the second differences, since we're talking about polynomials. And we get -1 minus -3. And if we subtract those two, we end up with the number 2. If we do 1 minus -1, that also gives me 2. 3 minus 1 is 2, and 5 minus 3 is 2. We see that the second differences are all the same, and this actually tells us that we have a quadratic relationship. So now we're going to take some time and look at graphs of various polynomial functions. So copy and complete the table below. We're going to use Desmos to graph each of the polynomial functions. And one thing you might want to do is adjust the window settings in Desmos so the intervals for x are from -5 to 5 and the intervals for y are from -5 to 5 as well. So I'll show you how to do that now. So first off, we're going to go to Desmos. We're going to click on Graphing Calculator. And once there, inside a blank item box, you can type in your function or use the keypad in Desmos. So for example, f of x equals -x to the exponent 3 plus 2x minus 1. So there's our cubic function. And to change the scale, you come over to the wrench and click on Graph Settings. We can go down to the x-axis and change this from -5 to +5. And for the y-axis, do the same thing from -5 to +5. And if you do that, that should give you a clear picture of all the functions in your assignment. So once you've completed the table, question 2 is going to ask you to make a conjecture or a conclusion about the degree of a polynomial function and its range. And then question 3 is going to ask you which polynomial functions have similar graphical characteristics and how are the equations of these functions related. Second part to this investigation is to look at finite differences. And once you've completed the investigation, then you should try the following questions.